Hello, everybody, and welcome to episode 4 in our Astronomy and Context series. This episode is called the Voyager Solution, and it's a remarkable bit of orbital mechanics. It is in orbital mechanics being the path, the trajectory that things like satellites or even anything in orbit takes through space. So let's go ahead and take a look at what's going on with this Voyager solution, because what we're really trying to contextualize here are the concepts that we just learned in Unit 1, Part 3, which remember that we studied Kepler's laws of planetary motion and then how Newton modified those by his just general laws of motion and his general idea of the gravitational force. And from that, we were able to come up with ideas like surface gravity, orbital velocity, so we're already talking about orbits and the physics of it, celestial mechanics, escape velocities, and a myriad of other things that really controls how things are moving around within space. All right, so I can't think of a better example of really bringing home these relatively simple ideas that we covered in class to this beautiful grand solution of celestial mechanics that became the Voyager missions, the Voyager 1 and the Voyager 2 spacecraft. It was called the Grand Tour because the Voyager 2 spacecraft visited every outer solar system planet. Voyager 1 could have, but it only visited Jupiter and Saturn before it left or before it changed its trajectory and was on a path to leave out of the north part of our solar system. All right. So, what are we trying to really contextualize? And I know this is supposed to be fun videos. What am I doing throwing up equations? Well, I wanted to show you that we have these equations, mostly orbital velocity and escape velocity, that are relatively simple for us to understand. And we studied this in this past Unit 1, Part 3 of our class. So orbital velocity, what was that? Orbital velocity, so let's take the Earth. The orbital velocity of the Earth is how fast does the Earth have to move at so that it continually falls towards the sun without ever hitting it. It travels in a circular-ish path and it is forever falling towards the sun and never hitting it. It is in orbit. And we needed to have that exact velocity so that the gravitational force between the Earth and the sun for the distance that the Earth is away from the sun becomes the centripetal force, which is also called the central seeking force, which is the force to keep something moving in a circle. You do a bunch of algebra and derive, and you get this orbital velocity. It's just the speed that you need to give something so that it'll be in orbit. So whenever we say we put up a GPS satellite or we send astronauts to the ISS, what we have to do is we have to design a rocket that will blast off from the Earth and then change let's say we're going to the ISS, we all have to change the speed of the capsule that's carrying the astronauts to be the orbital velocity at about 400 kilometers above our head, where the ISS is. So then it can rendezvous and meet up with the ISS, and you can put the astronauts onto this space station that's orbiting around the Earth. Sounds simple, right? But if you've ever played Kerbal, you know it's not so simple. And then we have escape velocity. And construction, or at least the equation, very, very similar looking to the orbital velocity, but it's a little bit bigger. Remember that escape velocity here is how fast would I have to throw this ball so that it would forever leave the Earth? So maybe we don't want to call this something like escape velocity because that sounds weird and it's not really a velocity, it's a speed. So I'm going to rechristen this the yeet velocity or the yeet speed, even better. So the yeet speed is pew, yeet. How fast would I have to throw that ball so it'd leave the Earth and never come back? For the Earth, that's 11.2 kilometers per second. Whenever we're going to talk about the Voyager mission, not only did we have to give it a speed, an escape velocity greater than 11.2 kilometers per second so it could leave Earth's gravity, but then we also have to make sure that these spacecraft, as they move further and further away from the sun, are moving fast enough to escape the sun's gravity. So you can see there's a lot of things that need to go on in here. Now, something I didn't introduce in class is what's called the vis-viva equation. It's basically the advanced version of orbital velocity. Notice that it looks very similar to the orbital velocity equation, except the vis-viva equation gives you the instantaneous velocity of an object on an elliptical orbit. Just remember that we studied that elliptical orbits. So when something is moving on an elliptical orbit, it's moving fastest when it's closest to the sun at perihelion, is moving slowest when it's farthest away from the sun at aphelion. Thank you, Kepler's second law of planetary motion. So we know that how fast something is moving whenever it orbits isn't always the orbital velocity. We want to know, given, hey, you're this far away from the sun, you're at this position in your orbit, how fast are you moving? What is your current speed? And the vis viva equation gives us that. Notice that it actually brings in some elliptical geometry here because we have this 1 divided by the semi-major axis right here. And here our r is current distance away from the sun, if we're talking about things moving around in our solar system. And then m here would be the mass of the sun for things moving in our solar system. And g, big G here, would be the gravitational constant. All right, so that's the vis viva equation. And oddly enough, people frequently ask, what is my favorite equation? And I always go with the vis viva equation because that's a cool name. And it's a cool equation. And it summarizes so much of celestial mechanics and how we actually can design and plan missions to visit other worlds in our solar system. Whether they're asteroids, planets, or moons of planets, whether they're inner planets or outer planets, or maybe like the Parker Solar Probe, even putting in something in orbit around the sun itself so we can study the sun. And also, so the vis viva equation not only sounds cool, but it literally translates, the Latin for vis viva would be the living force equation. Can't come up with a better name than that. Okay, so this is what we're all trying to contextualize, and you really can't do a better job with that other than the Voyager mission. But we have to talk about one other celestial mechanics thing that's absolutely fascinating, and it's called the gravitational slingshot, a bread and butter maneuver now in celestial mechanics that we did not know of until the 1960s, until Michael Minovich came up with a solution, or a numerical computational solution, to an age-old physics problem called the three-body problem. You've probably heard about the three-body problem. Maybe you've heard about the sci-fi novel, super cool. But the three-body problem is this classical problem in physics that deals with orbital mechanics. And the idea is, once you have three objects that are gravitationally interacting with one another, you can't really predict the trajectories, especially of the smallest, least massive one that's feeling the tugs of gravity the hardest. It's having the biggest change in its accelerations. So a classic example of the three-body problem might be you have the sun, then you have some other planet in the solar system, and you're flying a satellite nearby. There is no analytical solution. You can't write down an equation to solve this. This has plagued people since we've been considering things. So since the time of Newton, Newton racked his brain and thought he could come up with a solution to the three-body problem. That was 300 years ago. We still don't have an analytical solution. But Michael Minovich, as a NASA intern, he was a PhD student in mathematics, came up with a numerical way to solve the three-body problem. So you can give it specific inputs, and then you can use a computer to have it tell you the solution to the three-body problem. You can simulate it. So Michael Minovich comes up with a solution to the three-body problem, and he uses it to discover this amazing maneuver that we call the gravitational assist, or even better, the gravitational slingshot. And it's a way to change the speed and direction of a spacecraft for free. Well, you steal some angular momentum from a planet, or you give a planet some angular momentum, or some other third body, some angular momentum. But the net result is you change the speed and direction of a spacecraft. Because prior to this, we wanted to explore the outer solar system. We were starting to explore the inner solar system, but based on how much fuel we could put on our rockets, how powerful could we build our rockets, we just couldn't get a satellite up to the speeds required to get past the escape speed of the sun, escape velocity of the sun, launching from Earth, or really a viable way to get to the outer solar system in less than decades, like 30 or 40 years. We needed a way to really ramp up the speeds, and Michael Minovich comes up with this gravitational slingshot maneuver. And you can see some examples over here. So the sun's not shown here, but the satellite would be in blue, the spacecraft, and then we'd have a planet being in black. And it's going to approach the planet. Gravity's going to pull it towards the planet. So it's getting closer, it gets pulled towards it, speeds up, but it just arcs around it. And the net result is it speeds off in a different direction at a higher speed. And this is just one example. This is in the sun frame, and this is what it'd look like from the planet frame. We'll see lots of examples of this. So essentially, this provides a way to give a satellite a whole bunch of velocity to speed it up so it can get to the outer solar system in a hurry. Super cool discovery. You'd think that NASA would have fallen all over itself about how important and amazing this discovery is, but unfortunately, it was not really recognized whenever he came up with it because the Apollo program was going on, and that was sort of a big deal, putting people on the moon. So we have to wait not that long for a new solution to come up. And I just want to show you here are some other gravitational slingshots. So notice that we can speed up, slow down, change direction. We can borrow basically a little bit of energy, a little bit of momentum from a planet or an asteroid and send off a spacecraft in a variety of really, really clever ways. Cool maneuver. Thank you, Michael Minovich. Really thank you to Gary Flandreau, another NASA intern who was a spaceflight engineer, a spacecraft engineer. Well, as a NASA intern, he really liked the Minovich gravitational slingshot maneuver, and he started to use the same code, the same computational code on the same computers that Minovich was using, and he started to look at potential ways to go out and explore the solar system. Just like, hey, it would be a fun project. What are ways we could use this gravitational slingshot to go out and explore the solar system? And in doing so, he discovers a rare opportunity. So he's doing this in the mid to late 60s. And in 1965, he discovers this awesome, 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 awesome solution. A very rare opportunity, a solution to the three-body problem, a celestial mechanics wonder that if you launch a rocket in 1977 with the right velocity, that it has the possibility to visit all 4 outer planets, Jupiter, Saturn, Uranus, and Neptune, all within a 12-year mission timeline. This is amazing. This gets past the problems of trying to get out to the outer solar system. For the first time, we have a way to really go out and explore and visit the outer planets. And here's an opportunity of opportunities. Visit all the planets in one go. This is a very rare opportunity. It only happens once every 176 years. So we're not going to get another opportunity to plan a mission like the Voyager missions until 2153. The problem, however, is he's finding this out really close to, oh, if we want to use this, we got to go now. We have to start working now. So he starts working with Minovich, and they bring this to NASA, and they convince NASA that, okay, this is a once in 3 lifetimes opportunity. We must do something. So NASA gets to work in 1972, only 5 years to get this thing off the ground, on what they were calling the Mariner, which was a long series of missions exploring the solar system, the Mariner Jupiter-Saturn mission, the MJS, which fortunately in 1977, the launch year, got rechristened as the Voyager program. And what they decided is to create 2 spacecraft, Voyager 1 and Voyager 2. Because while the solution is great mathematically, reality is a lot tougher. So what happens if we send one Voyager spacecraft out, and just based on the errors of actually trying to get this thing to Jupiter and Saturn, that we miss a little bit, and therefore we wouldn't have the opportunity to go out to the outer planets? Or even more so, they really wanted to target a moon of Saturn. What happens if, in trying to fly by a moon of Saturn, Titan, which has an atmosphere that's thicker than Earth's atmosphere, and really they wanted to make sure, okay, Voyager must go past Titan. We have to explore this moon with an atmosphere thicker than Earth's atmosphere. We knew it had an atmosphere made out of nitrogen, so a very Earth-like atmosphere as far as we could tell, because the main gas that you are breathing right now in this room is nitrogen gas. We're like, we got to study this. Well, what happens if the Voyager spacecraft gets there, and because maneuvering is a lot harder than math, that it misses? Well, you better have a backup. So they sent two spacecraft, Voyager 1 and Voyager 2. Voyager 1 was Jupiter Saturn with a target of Titan. It's going to use gravitational slingshots to get there. Voyager 2, if Voyager 1 missed Titan, would change its mission plan to make sure it visited Titan or flew by Titan. Fortunately, Voyager 1 did not miss because NASA's good at what they do, and it flew by Titan as planned. So Voyager 2 continued with its original mission plan to give our first and only to today visit to the two outermost planets, Uranus and Neptune. We've only visited them up close by one spacecraft, and that was Voyager 2. It all comes down to this amazing solution of celestial mechanics that really boils down to understanding how things orbit, understanding things like orbital velocity and escape velocity, and then using some cool computers to come up with a solution to weave a spacecraft through the solar system. All right, let's take a look. I'm talking a lot about orbits. We should take a look. Here's Voyager 1's path. So Voyager 1 is in magenta. There's a gravitational assist at Jupiter. So notice it changes direction. Now it's moving a lot faster. And this is going to go to Saturn. And boom, it visited Saturn. Now you can see these lines right here. It actually starts leaving up and out of the north of the solar system. So here it reaches Jupiter in March of '79. Gravitational assist gives it that extra boost so it can reach Saturn just a year later. So that got a huge kick in speed because that's about 5 AU. Jupiter's orbit is about 5 AU from the sun, and Saturn's about 10 AU. And then it did a couple of other things. It took the famous pale blue dot photo of Carl Sagan fame in 1990. And then is now exited the magnetic influence of the sun. It has entered into interstellar space whenever it passed through the terminal shock, and then went through this thing called the heliosheath, where basically the solar wind of the sun, these particles that the sun is always streaming off, meet their end where the pressure of the particles from all the other stars in our local area in our galaxy push against that. And it transitioned into where the particles and the gases that are out there are not dominated by the solar wind and created by the output of the sun, but rather are the gases of interstellar space. And it entered interstellar space in August of 2012. That is Voyager 1, the two-planet one. I bet this would be cool for Voyager 2. So now we have same coloring for magenta, and then Jupiter's in green, Saturn's in blue, Uranus is in yellow, Neptune is in red. Now you can see that it's traveling down out through the south of the solar system. So again, let's watch it one more time since we know what the orbits are now. Leaves Earth, gravity assist at Jupiter, gravity assist at Saturn to make it so it can intersect Uranus, and then rendezvous with Neptune, and then get yeeted right out of the solar system. These 2D views of the orbital paths of Voyager 2 and Voyager 1 are fantastic to watch. But what about the three-dimensional view? Because you have to remember that our solar system is in 3 dimensions. And now we can even see that right here that we have Voyager 2 going down south out of the solar system. So I want to go ahead and share with you a video of a 3-dimensional view of the Voyager celestial mechanics solution. All right, so here it is, the grand tour. Voyager 2 was launched in August of 1977, a little bit before Voyager 1, which was launched in September of 1977. What we're going to do is we're going to track them as they make their journey through space. There they go. Voyager 2 is launched, and right about now, Voyager 1 is to be launched. This video follows Voyager 2 because it does the grand tour through the entire outer solar system, visiting Jupiter, Saturn, Uranus, and Neptune. There we have Voyager 1. What they did is they strapped these things to really, really powerful rockets, gave it the biggest delta V, the biggest velocity they could. Didn't even have to use a gravitational slingshot with Mars, and they were just blasted so they could reach all the way out to Jupiter, where they'll use a gravitational slingshot to redirect themselves to Saturn. Now, notice Voyager 1 is now going to pull ahead, and it's actually going to encounter uh, Jupiter first. It is the faster of the two spacecraft. And all this was designed, the launch times were designed so that you could have a celestial mechanics solution so that it could pull off this grand tour and visitation to all the planets. All right, so going through the asteroid belt, can't see asteroids. There it is, the interaction with Jupiter. And there's Voyager 2. And what I was saying about the asteroid belt, yeah, we always see in movies there's a whole bunch of asteroids. The asteroid belt between Mars and Jupiter. No, you can't really see them. They're too far apart. And yeet! There goes Voyager 1. Bye bye! It's heading up north out of the solar system. And Voyager 2 uses his gravitational slingshot at Saturn. And in the entire time, each one of these planetary encounters has a list of objectives. Now it gets to go to Uranus. And finally, it gets to reach Neptune. And there it's yeet out of the solar system, where it travels over the North Pole and takes a gravitational slingshot to sling it down to the south, heading out towards the constellation Sagittarius from our point of view. And what they're showing here with these weird ethereal celestial spheres is it's passing uh, the terminal shock and going into the helio sheath. And now it's passing through the helio sheath. And it's actually to the point where it's exited the other side. So both Voyager 1 and Voyager 2 are in interstellar space. That's what I was trying to show right there. So cool. And all of this from simple things that we've learned with orbital mechanics that we have seen by understanding things like escape velocity and orbits. Thank you, Kepler. Thank you, Newton, for modifying those equations. Thank you for understanding gravity. Now, that's enough, I think, for this entire astronomy and context so you can appreciate how cool celestial mechanics is. And really, whenever I'm saying celestial mechanics, I'm talking about how gravity creates orbits and trajectories through space so we can create really, really cool space missions. And Voyager pretty much is one of the coolest of all time. We don't get another chance for a really, really, really long time to do something similar. And still to this date, the only day is visited that we've visited up close the outer planets with Voyager 2. So that would be enough for a video, but it would just be remiss of me to not show you some of the video, the remarkable stuff. So at the Jupiter encounter, this is Voyager 1 approaching Jupiter. You can see the swirling of the Great Red Spot. Remember that this is way back. So it's Jupiter encounter. We're talking about 1979. And here's just one of my favorite pictures of Jupiter. Voyager 2 took this picture. This right here is the innermost Galilean moon of Jupiter called Io. And one of the things that Voyager discovered is Voyager 1 saw that there were active erupting volcanoes on Io. And Voyager 2 saw that those volcanoes were still erupting. Absolutely bonkers stuff. And we now know Io to be the most volcanically active object in the solar system due to its tidal heating effect that it gets from Jupiter and its own elliptical orbit. And it kind of has this yellowish color because it's covered in sulfur from volcanic output. And not only did we get these wonderful views of Jupiter and discover that Io is a volcanic moon, we also discovered that Europa has active geology, which we now know is an icy shell over a liquid water ocean. Voyager discovered the rings of Jupiter, and it discovered a myriad of moons of Jupiter. So pretty big stuff for its visitation to Jupiter. Voyager's at Saturn, some pretty cool discoveries. And here's it's at its approach. We get to see some of the rings up close for the first time. So we're discovering new rings. We discover these really cool, there's predicted that there are these types of moon called shepherding moons that exist interior and exterior to this very thin ring called the F ring. And we were wondering, why is it so thin? It's predicted that there are these small moons that basically constrain and keep all that ring material bound between the orbits of those moons. So we have the two shepherding moons, Prometheus and Pandora, discovered during the Voyager mission. And we get our first up close look. Here is that moon of Saturn, Titan. Titan is bigger than the planet Mercury, has an atmosphere thicker than Earth's atmosphere, which you can see here. You can see that it has atmospheric layers. The atmosphere is made out of nitrogen gas, and it also has liquid on its surface, not discovered by the Voyager missions. We have to wait for Cassini, which was not that long ago, historically, the past decade. We have to wait for Cassini to really get there to discover that it has lakes of ethane and methane, stuff like lighter fluid, and a full rain cycle and snow of ethane and methane. Super, super cool moon. All right, so Voyager 1 leaves us. It's now heading north out towards the constellation of Ophiuchus, out of the north part of our solar system, using the Earth to define directions. But Voyager 2 gives us our first, and to this day, only up close view of Uranus. And here it is. It's got this sort of wonderful cyan, a little bit greenish color due to methane that it has. Uranus is an ice giant planet. We just thought it was a gas giant up to this point, and we're going to continue thinking that it's a gas giant planet till we can really figure out that these moons that we thought were just enriched in things like methane are enriched in things like methane as ices, and that's the majority of their mass. So now we call them the ice giants instead of gas giants. That's more modern though. But here's our first up close view of Uranus, and it looks kind of boring until you start to see, oh, you can see some clouds and some activity going on. Here is a picture of its moon Ariel, which you can see has a geologically young surface. Super interesting. Lots it discovered, I think, 11 moons of Uranus. And it discovered 2 new rings of Uranus. It also discovered that the magnetic field of Uranus, which is the rotation axis of Uranus, is tipped on its side. So it's spinning around and around like this, but its magnetic field is not oriented in the same way. It's not tipped over at 90 degrees like the rotation axis. It's at a more moderate tilt. So the rotation axis and the magnetic field are offset from one another by a lot. Really, really interesting find. All right, Voyager 2 is going to continue on, and here we're getting our first up-close views of Neptune. All the images that are showing you are from the Voyager mission. And Neptune has this deep blue color, again due to methane, but it's colder, so it's going to be slightly different, have a slightly different interaction with light, because it's going to have slightly different properties at a much colder temperature, and it has a slightly different mix of ices. But another ice giant planet. You can see it has some cirrus clouds. That's the white going on there. We have this great dark spot that was discovered. It also targeted, we already knew about the moon Triton, which is larger than Pluto, the planet, and very similar in surface composition. In fact, Triton is believed to be a captured Kuiper Belt object. It's thought that Triton didn't really form with Neptune, it was captured later on. So, got our first up close moon of this really cool moon Triton, bigger than Pluto. And we discovered 2 new rings of Neptune. And I'm just giving you a couple of the highlights. Of course, it did so much more. It investigated the magnetic field of Neptune as well. And remember that this is where it passed over the North Pole and used a gravitational slingshot to get slung towards the south, leaving the solar system to the south, heading towards the constellation Sagittarius. And to bring it all back around before I just give you some nice flavor text at the end or flavor videos at the end, will they escape? Because really, this is contextualizing things like escape velocity. So why don't I do some calculations for you? Voyager 1, its current distance is it's 152 astronomical units away from the sun, the farthest man-made object. It's technically in interstellar space. So good job, Voyager 1, being a pioneer for humanity. Just put that in meters so I can actually plug it into this equation. And we want to compare the escape velocity given its distance away from the sun. So we have the mass of the sun, how far away it is from the sun, which determines how much speed it needs to escape the sun's gravity. And what we're going to do is calculate that out. So I can crunch those numbers, plug in all the appropriate things. So you get that the escape velocity for its current position is about 3,420 meters per second. If it's moving faster than that, it will escape the sun's gravity and never come back. It'll leave the solar system and no longer be a part of our solar system bound to our sun. Its current speed, 17,000 meters per second, well above the escape velocity for the sun at the distance that it's at. And then we have Voyager 2, can do the same thing. There's current distances, convert that to meters. Here's its current speed, plug all the numbers into the escape velocity. So what is the escape speed for the distance of 127 AU? 3,740 meters per second. It's traveling a lot faster than that, about 4 times faster than that. So yes, these are leaving the solar system and they're never coming back. They will escape the gravitational pull of the sun. And finally, just because the slingshot is so cool and to give you a real appreciation of what these people, these celestial mechanics people, they're designing our space missions. Here's the Cassini mission. So I've color coded Cassini is in magenta using a number of gravitational assists, the little one with Jupiter right there to rendezvous with Saturn. This is a flagship mission that was in orbit around Saturn for a decade. And there it is now traveling with Saturn. But notice that it's using multiple things, including an asteroid, gravitational assist, gravitational assist, gravitational assist, gravitational assist to reach its target. That's a pretty clever way to get out to Saturn, especially whenever we don't have rockets that we can just launch something directly to Saturn in a short amount of time. All right. Now, I want to just share one more with you because I know this is a long episode, but this one's just nuts. So I'm going to build it up a little bit first. We had, or the European Space Agency, so the collective we have humanity, had this amazing mission called Rosetta, where we sent a spacecraft to hit a impossible target, a small, several kilometer across comet, something that is so small that the gravity is weak enough where if you're standing on it, you could jump off of it. That's how low the surface gravity is. So imagine that we're going to sending a spacecraft from Earth to hit a few kilometer sized target out in outer space that barely has enough gravity to hold onto anything. So we have to insert it into orbit around that. So we have to adjust all the velocities through gravitational slingshots using fuel, things like that. A pretty remarkable, I mean, a lot of people do consider it almost an impossible shot. We pulled this off. So let's see the celestial mechanics of that one. Lots of players here. Magenta is our spacecraft. And we'll watch it a few times. Look at all those gravity assists, all those changes to orbits. Also, we have a perfect rendezvous with a comet where they can match their relative velocities and start traveling together so then it can start to go into orbit. It had to use several gravitational assists off of 2 different asteroids, asteroid Steins and asteroid Lutetia. Had to use gravitational assists, had to leave Earth, use gravitational assists of Earth, Mars, all to reach 67P Cherenkov-Gerasimenko. So, it looks pretty easy. Orbital velocity, not that bad. Vis viva, even not that bad. Escape velocity, I can get that. But then when you put all these moving parts together and our limitations of what we can actually build and the launch speeds that we can launch at, now you can see why we have very specific launch windows. We have to have a very specific amount of fuel on there. We have to have a very specific amount of weight we put on the rocket so that is the right amount of fuel to actually get it to the initial launch so it can do its initial rendezvous to get its initial gravitational assist. Get that just right, so make adjustments just perfectly so that then it can make its next gravitational assist and make its next gravitational assist, make its next gravitational assist so it can reach some target in our solar system. This is how important the concepts we studied in Unit 1, Part 3 are. I hope you enjoyed this episode. I will see you in the next one.